What we want to go over in this lecture is what happens when a first order low pass filter is insufficient. So we already know from our experience on the bandpass filter that if we cascade filters together, the overall transfer function is multiplicative. So in other words, if I cascade several identical low pass filters together, then my transfer function, if I have n of these, basically looks like n of these placed cascaded together. And so I take this transfer function of a single inverting op-amp low pass filter, which is -1 over s plus 1, and that'll be multiplied by itself n times. So it's -1 to the n power over s plus 1 to the n power. Now, as you know from Bode plots, that means that in the denominator in the numerator, we have a constant and we don't have any terms in s. So initially the response will be flat as shown in this figure. And then at omega equals 1, we have our cutoff frequency. So at the cutoff frequency, as you know, the first order filter comes down at a -3 dB point. And so the 1 in the prototype filter is actually the cutoff. So the first order filter Bode plot looks like this top line here, and the slope out here is -20 dB per decade. Now, as you know, that breakpoint occurs at this pole, and the slope depends on the slope above the breakpoint depends on the power of the pole or the order of the pole. So in this case, for the first order filter, it's just s plus 1, so we're -20 dB per decade. If it's s plus 1 squared, then the slope of a second order system would have -40 dB per decade, and the third order would be -60 dB per decade, and the fourth order would be -80 dB per decade, and so on. And as you also know, basically, when you come out here to where the slope is constant, there's an asymptotic line that extends back that intersects with the lower frequency asymptote at the frequency omega equals 1. So that's where the two asymptotes for the high frequency and the lower frequency behavior meet on a low pass filter, meets at the breakpoint. And then the actual curve, of course, is somewhat below that because remember the asymptote is an approximation that holds in either limit, the low frequency limit or the high frequency limit. So what that means is, and if I were able to draw on the chalkboard, I could really illustrate this clearly for you, but what that means is that as the filter gets higher and higher order, the offset at omega equals 1, or wherever the cutoff frequency is, for the first order is -3 dB, but for the second order is actually -6 dB, and so on, because the slope is steeper. When you draw the asymptotic line, it drops lower. Another way to look at that is to think about what happens when omega is equal to the cutoff frequency 1. So if, for example, we replace here in this magnitude calculation, instead of looking at this being 1 over the square root of 2, let's suppose we put 1 here and we let n equal 2. Then the magnitude would be actually 1/2. And if we then, because when we found the magnitude, so if you look at this formula and you let this be 1 and n is 2, then the magnitude is 1/2. If you let this be 1 and n is 3, then it's 1 over 2 to the 3/2 power, and so on. So in other words, this value for higher order filters is not equal to 1 over the square root of 2 or -3 dB. So that becomes a problem because independent of what this value is at omega equals 1, the definition of the cutoff frequency is -3 dB or 1 over the square root of 2. So the dashed line on this figure represents -3 dB. And what you can see is that as the filter gets higher and higher order, that moves lower and lower here in frequency. So basically the trade-off, now, so the good thing is you do get a steeper transition in the cutoff regime, but the bad news is that it's moving the cutoff frequency back, while the knee of the curve remains at omega equals 1. So you have less flatness in the passband, and you have more you have a rounder attenuation in the cutoff band. So if you're going to design a cascaded filter so that you can get this sharper attenuation, then what you need to have is you need to have a way to compensate. So what we're really doing, and let's take this fourth order curve as an example. What we really want to do is, if you look at where that curve crosses the 1 over the square root of 2 point, or the minus 3 dB line, we really want to design our filter to have a cutoff right here. If we do that, or we want to design our filter so that this point is actually equal to the 1. So we want to sort of design this by moving the whole thing forward so that this point moves up to 1. So the way to do that, first of all, is to figure out what this point is. So you can do that through some algebra by saying, independent of the order n, the definition of the cutoff frequency is that it's where the magnitude is 1 over the square root of 2. Do a little bit of calculation, and we find that for the nth order filter, what actually happens is the cutoff frequency moves back, and it moves back in frequency, and it moves back to this point. So first of all, this points out one of the reasons it's important to design a prototype filter is that it's a whole lot easier to understand what this means when our original design was for a cutoff of 1. So basically, this gives us a formula, and what it tells us is, where do we move from 1 when we design our higher order filter? So as an example, if you look at a fourth order filter and you use that formula on the previous page, so let's go back to that previous page. We're going to use this formula, and we're going to plug in n equals 4. And so what we're looking for is the value of this point right here in frequency. So when you do that, you find that you get 0.435 radians per second. So what that means is that when we now employ a scaling factor around a design, our original frequency for this fourth order filter is not going to be omega equals 1. It's actually going to be omega equals 0.435. So in scaling, we're actually trying to overcome two things. The first thing we're doing in the frequency scaling is to get to this 500 hertz, which would be 500 times 2 pi radians per second. And that would be our scaling factor if we had a first order filter. But since we have a fourth order filter, then what we need to do is we need to divide our desired frequency, which is 1000 pi radians per second, by 0.435. And when you do that, you get a frequency scale factor of 7,229.39. And then, of course, you can design your magnitude scaling factor as you normally would by using the appropriate values, given that you know your desired capacitor value, your original capacitor value was 1 farad, your frequency scaling factor was 7222.39. You can come up with a magnitude scaling factor, which ends up being 138.46 to give you the correct resistor value. So essentially then, and this particular design problem asks you to also calculate a passband gain. Now, as soon as you go beyond a first order filter, it's really a good idea to accomplish your gain by doing so with a separate inverting amplifier stage. So in actuality, in this design, we have 4 identical cascaded op-amp low-pass filters, and then we have a stage with an op-amp that basically accomplishes giving us the gain of 10. So given that we have a gain of 10 and our design frequency is 7222.39, this is what our transfer function looks like. So here is what the actual design of the system would look like. You have 4 stages here, and then this final stage has an error, as many things in this book does, so I want to apologize for that. Basically, the final stage, the goal is to get us a gain of 10. So either this needs to be 1384.6 or this needs to be 13.85. So please note that that's a typo in the book's materials. Okay, and finally then, this is what the Bode plot looks like. So note from the Bode plot, we do start out fairly flat. We do have a gain of 20 dB, which is the same as a multiplicative gain of 10. And if we look for that minus 3 dB point, which would be about right here, you can see that that comes pretty close to that 500 hertz design. It's a little bit hard to see exactly where 500 occurs, but it's roughly right there. And then we can also see, so kind of a quick and dirty way to tell what your attenuation is if you come over here. This one's really hard to tell because we don't get a full decade. If you go from 500 to 5,000, you can tell that you have roughly a drop of 80 dB, but once again, we really would need to see from 1,000 to 10,000. As you can see, this curve's kind of cut off. So kind of hard to tell how many dB per decade just from looking at this particular graph that this slope is. So one thing to keep in mind is if you are doing Bode plots and you do want to look at attenuation in the transition band, you want to be sure your plot covers enough so that you can fully see how many dB per decade. Sometimes on exams, rather than asking you to draw a Bode plot, I might give you a Bode plot that looks kind of like this and ask you what the filter order is. If I were to do that, I'd have to be sure, for this one at least, since this is a 80 dB per decade drop, I'd have to be sure I really gave you enough room on the plot here to be able to see the full a full decade, so that you knew sort of how many dB you dropped along that decade. So anyway, this is important. So let's go back. So here's what the system looks like. You notice these four are all identical. The reason to do that is so that we can get this steeper transition, so that we drop off pretty rapidly and attenuate higher frequencies pretty rapidly. The engineering cost of doing that is that as this slope out here gets more steep, then the curved line that follows those two asymptotes drops with more curvature back into what should be the passband, and you get a little more flatness in the attenuation band, and it's just because of the way it drops below where the two asymptotes meet. So the first order filter is obviously much smoother. You're designing around a prototype cutoff frequency and scaling directly around omega equals 1. For higher orders, you have to figure out at that higher order, where is your new cutoff frequency? It's not going to be 1. It's going to be whatever this formula tells you for a given order in. So the advantage of this, faster cutoff. The disadvantage, your cutoff frequency changes depending on the order of filter. And you get this kind of pretty severely sloped kind of behavior out of the curve. So the solution to that is to go with a different type of filter. Really, once you get above about second order, you can see this effect becomes pretty dramatic. So much above a second order low pass filter, many people believe that you're better served going with a Butterworth design, because a Butterworth has the effect of keeping you flatter in the passband, yet also having a sharp attenuation based on the order of Butterworth that you design. The only thing about a Butterworth filter is it's basically just it's a different kind of circuit, and it's a different kind of transfer function. So in the next set of lectures, we will go over Butterworth filters, but I think it's important to look at the cascaded op-amp filter first, because then you can sort of see really clearly why you need to even worry about designing a Butterworth filter.